In some situations, it's easier to design a controller or a filter using continuous S-domain transfer functions. We have a lot of mathematical tools that make analyzing and manipulating them easier than, say, their equivalent time-domain differential equations. However, while we like to work with transfer functions for design and analysis, it's often the case that we need to implement them in software that runs on some processor or microcontroller, and it might not be obvious how to go about doing this. So in this video, we're going to cover 4 simple ways to implement a transfer function in code. I'm Brian, and welcome to a MATLAB Tech Talk. Now, before we get into any of these methods, we need to talk briefly about continuous time and discrete time systems. Transfer functions are continuous time functions, so they produce a continuously changing signal in the time domain. But software runs in discrete time. At each time step, the code runs and the variables are updated. And then those values are held until the next time step when the code runs again and they're updated once more. So the variables in a discrete system are only updated periodically. Why is this a big deal? Well, when we implement a transfer function in code, we're basically implementing a differential equation, which means that we need to perform differentiation and integration. And since we only have periodic information in software, we have to figure out how to integrate the signal and differentiate the signal using these discrete points. There are many different ways to do this. And to just illustrate a few, let's say that we want to find the area under this continuous curve, and we're sampling the signal at discrete time steps. The question is, how can we sum up the area under this curve if all we have access to are these data points? Well, a simple way is to just assume the value of the signal is held constant between time steps, and so the area is just the sum of all of those signal values times the delta time. This is a first-order method called forward Euler integration, and it typically produces the most error, as you can see by the fact that it's grossly over or underestimating the area. We can decrease this error by lowering the sample time, which means that we're holding the value constant for a shorter time before the code runs again and updates the variables. But the lower the sample time, the less time we have to run the code since it has to finish running in this amount of time. So there's a limit to how short we can make it. In addition to lowering the sample time, we can also decrease error by choosing a different integration method. Other methods make different assumptions as to how the signal is changing between the discrete points. For example, second-order trapezoidal integration assumes that the signal is linearly transitioning from the previous time step to the current time step, and then it calculates the area of these polygons. And there's a number of higher-order methods that use more of the past data points to try to create a more accurate representation of what the signal is doing between time steps. Typically, the higher the order, the better the result. Discrete differentiation is similar. A simple way to find the slope between two discrete points is to just subtract the two values and divide by the sample time. And just like with integration, we can improve this with higher order methods or by lowering the time between discrete points. So hopefully you can see how the accuracy of our code is going to depend on both the sample time, how fast the discrete points are updated, and the integration and differentiation methods that we choose. So these are 2 things that you need to consider when writing a continuous transfer function with discrete time software. Now, with that being said, in the code that I'm going to show you, I've just picked an arbitrary sample time and an arbitrary differentiation and integration method. But when you write your own code, you can choose a different sample time, and you can swap out the discrete methods for something else. It all depends on how accurate you want the result and how much processing power and memory the microcontroller has that you're working with. So let's get to it. For the first method, we're going to talk about numerically solving the differential equations. A transfer function is a differential equation that's represented in the S-domain rather than the time domain. And since our code is going to execute in the time domain, we're going to want to get it back to the differential equations with the inverse Laplace transform. For example, we can multiply out the numerator and denominator and take the inverse Laplace transform to get this differential equation. The second derivative of y plus the first derivative of y plus 2 times y equals the first derivative of u plus 2 times u, where u is the input signal and y is the output signal. Taking the inverse Laplace transform like this is really easy because it can be done by inspection. Every s multiplied by the variable is just another derivative of that variable. So s squared times y is the second derivative of y, and s times y is the first derivative. And in differential equations class, you may be asked to solve for y of t analytically, but with software we can find an approximate solution numerically, and that's what we're going to do. To do this, we can rewrite the differential equation so that the highest derivative of the output is on the left side and the rest is on the right side. The basic idea for how we're going to approach this code is this. In the very first time step, we'll just solve for y double dot with our differential equation. Then in the next time step, we're going to integrate that y double dot to get y dot, and then we'll integrate y dot to get y. The input u is what's passed to the transfer function, so we always have a current u, and we can take the derivative of that to get u dot. Okay, so now we have all of the information we need to solve for y double dot again, and then we can move on to the next time step, and the process just repeats itself. And this works perfectly fine for every time step. But as you can see, it doesn't work for the first one, since at the beginning we don't have y double dot to integrate, which means we don't have y or y dot, and we also can't determine how the input is changing from a single discrete input point. So we're missing 3/4 of our equation. But that's okay. We can just set these three to an initial value of our choosing, and we're all set. So there it is. A simple way to use discrete differentiation and integration to numerically solve a differential equation. Let me show you one version of this code in MATLAB. And if you're looking for C code or something else that you can run embedded on a microcontroller, this hopefully will give you a good starting point to understanding the logic. Now at the beginning here, to get the true response, I'm going to use MATLAB's ability to handle continuous functions and plot the step response for our S-domain transfer function, s plus 2 over s squared plus s plus 2. And then we're going to compare each of our discrete methods to this one just to see how they do. Okay, on to the first method. Here we build the time vector with a sample time of 0.1 seconds, and then use that time vector to build the step input. We set the initial conditions and predefine the size of the input and output vectors so that they aren't changing size each iteration in the for loop. Inside the for loop is where we code the differential equation. For the first step, we have to set the values to the initial conditions, like we said, but then we can solve for the second derivative of y. And then every other time step, we can just solve for u dot, y dot, and y using a derivative and two integrals. I'm using first order methods for differentiation and integration here, but again, this is where you can replace this with a higher order method of your choosing. And we can see that the result for this is okay. It follows the general shape of the true response, but the magnitude is a bit off. But let me change the sample time to 10 milliseconds, 10 times faster, just to show you the impact sample time has on the accuracy of the result. I'll rerun the script and it'll update the graph. There we go. See, this looks much better than it did before. So numerically solving the differential equation like this is one way to code a transfer function. For the second method, we're going to convert the transfer function to a state space model first. Setting up multiple derivatives and integrals in your code like we just did is straightforward, but each time they run, they add a little more error into the solution. So we do well to try to remove them where we can. And it turns out, if we set up the problem differently, we don't need the derivative at all. We can solve the problem with just a single integral that operates on the two-element state vector. To do this, we need to convert our transfer function into state space representation. And there are simple ways to go from a transfer function to state space with hand calculations, but for us, we're just going to do that transformation with the ss command in MATLAB. This representation takes a high-order differential equation and breaks it up into a number of first-order differential equations. And if the differential equations are linear, which they're going to be since transfer functions are linear, then we can package them into matrix form. And I'm going to come back to the values of these matrices in just a second. Just realize that for state space representation, we only need 4 matrices, A, B, C, and D. You can find a MATLAB Tech Talk video on statespace in the description if you want more information. But for the purpose of generating code, I'm going to give you this really fast introduction. We have two equations. The first is the state equation, and it shows how the state vector changes over time. So how x dot varies based on the state vector x and the input vector u. So knowing x and u, we can solve for x dot. The states, however, aren't necessarily the variables that we want to output, so the output equation gives us y. And y is a linear combination of the state vector and the input vector as well. So with these two equations, it's pretty straightforward to write the code. To begin, we initialize the state vector to some initial condition. Then in the first step, we use the initial states and the input to solve for x dot and the output y. Then in the next step, we integrate x dot to give us the new state vector for this time step, and we use it and the input to again solve for x dot and y. Then we rerun the whole process over and over. So let's check out the MATLAB code for this method. Here I've defined the A, B, C, and D matrices using the values that we got earlier. Then we set the initial states and once again predefine the vector sizes. Now we can step through solving the set of first-order differential equations. In the first step, we set everything to the initial conditions, but for every other step, we integrate x dot to get x, and then we use that and the current input u to get the next x dot and output y. So in this way, we only need to code a single integrator, which makes the code easier to read, and we're only integrating the two states in our state vector. So that's one less differential operation than we needed in method 1. And as you can see, the result is very nearly the same as with the other method, so our math is working. But if we zoom in, you can see that with this method, it produces a result that is actually slightly closer to the truth than the first method. And that is all because we're not adding the additional error that comes from the extra discrete derivative operation. Okay, for the third method, we're going to convert the transfer function first to the z domain. Both of the previous two methods converted the transfer function to continuous differential equations that we then discretized when we converted it to code. However, in this third method, we're going to do that discretization first by converting the transfer function to the z domain. And there are a number of different methods for going from an S domain transfer function to a Z domain transfer function, and I've linked to a video series that goes over several of the more popular methods if you want to check it out. But to convert our transfer function, we're just going to use the C to D function, or the continuous to discrete function, in MATLAB. With C to D, we have to pass it the function that we want to convert, of course, but we also have to select the sample time and the discretization method, which is effectively the integration method that we want to use. This means that the sample time and integration method are already built in when we have a Z transfer function, so we don't have to worry about writing our own integrator in code. But we do have to make sure that we run the resulting difference equation with the sample time that we used to create it. So if we want to change the sample time or the discretization method, we have to create a new Z transfer function. This particular one is the result of a 10 millisecond sample time and the Tustin discretization method. The Tustin method is equivalent to saying that we're using second-order trapezoidal integration. Again, the linked videos below show why this is the case. Now, we want to get this transfer function back into the time domain to write it in code. But luckily, it's just as easy as it was with the inverse Laplace transform in the first method. The inverse Z transform of 1 over Z is a one sample delay. So if you have y over u equals 1 plus 1 over z, we could take the inverse Z transform to get that the output y is the current input plus the input from one step earlier. Since it's this easy, we can essentially just do the conversion in our head and write out what the time domain equivalent is directly. For our transfer function, we don't have any obvious 1 over z's anywhere, but we can divide the numerator and denominator each by z squared to write this as rational expressions of inverse z. Alternatively, in MATLAB, we could just change the displayed transfer function to use z inverse as the variable with this command. To convert to a time domain difference equation, we can easily take the inverse Z transform like this. We just replace each Z inverse with a unit delay, and then solve for y. Or in other words, the output y is equal to 0.005 times the current input plus 9.95 e to the minus 5 times the input from one sample ago, since there's a single 1 over z, and then minus 0.005 times the input from two sample times ago, since there are two 1 over z's, and so on. Now, in code, we can solve this difference equation in almost the exact same way that we did in the first two methods when we solved continuous differential equations. We just choose the initial conditions and solve for y. So let's look at the code for this method. To begin, we set up the time vector and the step input, and then we initialize the variables. But since our particular difference equation is using the two past values for both the input and the output, we have to initialize all four of these values. And the for loop is still where we're solving the difference equations each time step, but we have to handle the initial conditions for the first two steps. And then for each step afterwards, we're just multiplying and adding values together. You can see that the output is just a function of the last three inputs and the last two outputs. Again, we don't have to explicitly code any integrators with this method since it's already taken care of in the z-transform process. Okay, and check out this response. It looks really good. And if I zoom in, you can see that it's almost perfectly on top of the true response. Now, I don't want this response to fool you into thinking that this is the most accurate way to implement a transfer function in code. It's only producing a better response than the other two, simply because the Tustin method that we used is equivalent to a second-order integrator, which we know is going to produce a better result than the first-order integrators that we used in the first two methods. If we upgraded the integrators in the previous two methods, then they're going to have better results as well. All right. Now, for the fourth method, we're going to talk about Autocode from MATLAB or Simulink. And I'm not going to go into too much depth on this method since there are other good resources for generating code automatically using MATLAB and Simulink. And I've linked to some of them in the description. I just want to point out that now that you know several different ways to code a transfer function by hand, you're going to have a better understanding of what autocoding is doing for us. Just like with writing code by hand, we still have to pick a sample time. And we still have to pick an integration method. But with autocode, the act of generating the C code is taken care of for you. This removes the possibility of making a mistake in the code, but it also allows you to more easily choose a higher order integration method with no extra effort on your part. You can just select from a number of built-in integration methods and you're all set. So that's where I'm going to leave this video. If you have a controller or a filter that you designed as a continuous function and you want to build C code or other code that is going to run on some other target hardware, hopefully you find one of these four methods helpful. And if you don't want to miss any future Tech Talk videos, don't forget to subscribe to this channel. And if you want to check out my channel, Control System Lectures, I cover more control theory topics there as well. Thanks for watching, and I'll see you next time.